So, hello everyone, and welcome to the live session. Today we are going to discuss reaction mechanism topic which we were discussing already. But today, in today's class, first of all, I will be covering the portion which we have left in the yesterday's class, that is case number 4 and miscellaneous part of the NGP reaction, and also we will discuss some questions regarding the substitution regarding reaction mechanism, the topic which we have covered. Generally, usually we will see the topics such as SN1 and I think some questions of SN2 mechanism also. So moving ahead in the session, we will first cover a little bit topic and few questions. Good morning to each one of you who have joined the live session. Welcome to the live. Good morning Praful, good morning Anju, good morning Mosby. Welcome to the live session, and you people already know that this lecture series is completely going to be in English medium so that the students should not face language as a barrier. Now, in today's session, we will discuss some previous year questions also, if time permits. Otherwise, I will be covering your concept. But because it's important to cover the concept once and question, you can practice on your own also, and I can schedule some extra sessions also for the question part. Okay. Good morning, spread peace. Good morning to each one of you who have joined the session, and welcome to the live session. My plan was to completely practice a question throughout this class, but since we are left with few portion of the previous class, so first of all, our target will be that to cover that portion. Moving ahead, let's first of all recall what we have studied in the previous lectures so that we can create a connect over that. In the yesterday's class, we have gone through a simple rearrangement that is called as Payne rearrangement, a very famous rearrangement which is asked in the exam also. Then the case number 3 of the bromine, we have seen that how bromine is behaving as a neighboring group and the OH group here is behaving as a living group, and the NGP reaction is taking place. I hope you have got this concept. We have used the conclusion which we have learned in the previous class in this question and concept, and we can, without drawing the product also, we can tell that yes, the product formed here are going to be identical. Good morning to each one of you who are joining the live right now. So I have given you one question homework also. I hope you have done this question. Can you tell me the answer in the comments? What about intermediates, whether it is an optically active, optically inactive? What about P and Q product? Are they identical? They are pair of enantiomer. All these information you must have written in your notes. Now, tell me fast, what is your answer? And then we will match our answers. I will be discussing this question and you will be matching your answer whether you have done it correctly or not. Optically active intermediate. Okay. And what about the products P and Q? What's the relationship between them? Products are identical and meso. Very good. Good morning, Deeksha. See, in this question, it is clear cut that we have a bromine group as a lone pair and a OH group in acidic condition, which is going to be protonated. It is going to have a positive charge and this will be acting as a living group. This is the scenario. Now, first of all, we need to convert this molecule into a staggered form because always the Fischer form is drawn into an eclipse form. So I will be drawing this bond, this violet color bond here. Both the CH3s are bent downwards, so I have a CH3 at this center and I have a CH3 at this center. Now we have two groups, one a Br at this center and one a OH which will be protonated is going to be at this center. Again, I will be having a hydrogen at this center and a hydrogen at this center. Correct? Now what we want is our Br group and OH group should be anti to each other. So keeping this bond here only, I will be placing my Br here and my OH which is protonated and is a living group will be here. So that the Br lone pair can very easily attack into the sigma star orbital. In order to do so, we must have done some sort of rotations also. See, the OH would have been shifted here. The CS3 would move this side and the hydrogen would move this side. So what is going to have is, we are going to have our hydrogen at this center and a CS3 group at this center. And the center that is backward, the Br will shift here, hydrogen shifts here, and the CS3 comes out. So what we see is, when I draw this product, I will be having my hydrogen at this center and CS3 moving outwards. So this is the correct scenario. Now, this Br lone pair is going to attack into the sigma star orbital and the water is going to be eliminated. So what we are going to draw is a three-membered cyclic intermediate with a bromonium ion and a CS3 which is placed above the plane here, and a hydrogen will be below the plane here. And at this center we are going to have a hydrogen that is above the plane and a CS3 that is below the plane. Now, when I draw a plane, let's suppose in the intermediate, this plane of symmetry is absent, and if it is absent, our intermediate is definitely optically active one, and if our intermediate is optically active, we can straightforward tell that the products which we are going to form when we will be attacking at both of these centers, the A center and the B center, is going to be optically active, or they are going to be optically inactive. See, whenever we have an optically active intermediates, the products are going to be, let us draw the product also. So when we attack at the A center, we will be having a Br here and the second Br at this center. Here we have above the plane hydrogen and a Br that is placed below the plane. Here we have a CS3 that is above the plane, and here we have a hydrogen that is below the plane. Now, when we attack at the B center, what we have is a Br at this center and the second Br will be here. Again, keeping the stereo as it is, we will be drawing, you will try to find a Y at these centers, a CS3 here and a hydrogen here. When we compare these two, we can very easily tell that yes, the product, okay, I have done something wrong. This is going to be our CS3 functional group. So we can very easily tell that yes, the products are going to be identical, homomers, or you can simply say the products are going to be same. Now you need to tell me whether the final solution is optically active or not. Yes, the products are identical. You have formed the product, but it's very important to realize whether the product form is a meso compound or it is not a meso compound. So in order to find any molecule, whether it satisfies the condition of meso or not, what are the conditions we look? Tell me, what are the conditions we look for a compound to be meso? Good morning to everyone who have joined late. In stereochemistry lectures, we learn what are the conditions to check a compound whether it falls into the category of meso or it does not falls into the category of meso. Very good, Rashi Jain. Sir, there should be at least two chiral centers and either plane of symmetry or center of symmetry. I will be writing the conditions here. The molecule should have internal plane of symmetry or it should have center of symmetry. Any one of them will be present, the task is done. And the second condition is it has at least two chiral centers. CC stands for chiral centers. Now, since they both are identical, I will be checking this one only. There are two chiral centers, no doubt, sir. Is there any plane of symmetry? So they are present in staggered form. Br and Br are anti to each other. There is no chance that there will be a plane of symmetry. Is there any chance of center of symmetry? If we sit at the center of the molecule, we will find that if we move this side, we get a Br. If we move this side, we get a Br. If we move this side, we get a CS3. If we move this side, again we get a CS3. If we move here, we get a hydrogen, and if we move here, again we get a hydrogen. It means sitting at the center of the molecule, if I start to move 180° in the opposite directions, I always get the same substituents. It means yes, with two chiral centers, molecule do have center of symmetry, so it will be a meso compound. And meso compounds are optically inactive, so the final solution is going to be an optically inactive one. Examiner can also give you options that are present in the Fisher form. So you should know the shortcut how you have to convert this wedge dash looking molecule into Fisher form into seconds. It should not be that you are finding RS configuration and then you are converting. It will take lot of time. You need to learn the shortcuts which will convert this wedge dash directly into the Fisher form within seconds. So this is the concept of stereochemistry which we learn in stereochemistry. I am taking a simple example to explain you. Let's suppose we have pick up this molecule, okay, this product, and we want to convert this into a Fisher form. So how we are going to do that? Let me take a blank slide. Yes, we have a BR at this center and we have a BR. There are lots of shortcut methods. If you have your own method, then it's very good. You can apply that also. And if you like what I am telling, you can apply that also. No problem. There is a hydrogen that is above the plane and a CH3 below the plane. At this center, we have a CH3 above the plane and a hydrogen that is below the plane. Now, I want to convert this molecule into Fisher form. What's the shortcut, sir? See, first of all, you need to draw a backbone of the Fisher molecule. This is going to be like this. Now, both the terminal centers are going to have a Br. So, one Br will be present here and a second will be present here. Now, the leftmost chiral center will be the bottommost chiral center. And if the leftmost center is pointing downward, then the above the plane valency, the valency that is present at the wedge is going to be at the right hand side. It means your hydrogen is going to come here. If your backbone is empty, it means in your backbone the sigma bonds are pointing opposite to each other. The above the plane valencies are going to go opposite to each other. It means here the above the plane was CS3, so CS3 is going to move at this center. Now, rest is fill in the blanks. The hydrogen along with a CS3 and a hydrogen present here, we can see that yes, this molecule has an internal plane of symmetry. So of course, and two chiral centers, so this will also be a meso compound. We can check in this form also, we can check in this form also. Here the symmetry element was center of symmetry, but once I have converted this into Fisher form, the symmetry element is plane of symmetry. Usually students get confused in these two forms. Is this clear? So you should be comfortable in conversions from Fisher to Sawhorse to Newman to, let's suppose, wedge dash. Finding RS will be a very long method. We will be not doing that. We will be applying some shortcuts. Okay. If you want to learn this concept of conversion, you can visit our same channel of IFAS chemistry, where you can have a playlist of stereochemistry with a name of One Stop Solution to Stereochemistry. In that, I have discussed a lot of these concepts and the basics of stereochemistry I have covered there. You can go and explore that also. Okay. But that will be in the Hindi medium. Means the language I will be using in will be a mixture of Hindi and English. Yes, if we rotate the molecule, then we get plane of symmetry. Very good, Rashi. But we generally don't prefer rotation. We generally prefer the form in which the molecule is. We have to check in that form only, because sometimes it creates confusion in our mind. Okay, so this was the homework question. Now I will be discussing few previous year questions. See, these are the type of questions which generally CSIR NET asks. Their level of questions is generally a little bit at the higher side. What they are saying is, you are given few substrates. Among the following, the compound that will be have highest rate for nucleophilic substitution through SN1 mechanism is. They have given you the mechanism. They are saying that we are going by an SN1 mechanism. Now you need to tell for which substrate the rate is going to be the fastest. I have explained you this concept into an SN1 reaction in the previous lectures when we were discussing SN1. Now the question is in front of you. It's very important. Students generally confuse and they tell that sir, A option will be correct. If you are not aware about the concept, then definitely I'm 100% sure you will be telling that sir, A option is going to be correct. But the situation is different. Steric hindrance, very good Diksha. The steric hindrance is going to be a dominant factor here, because in a SN1 reaction, the first step, or I can say the step which is the rate determining step, is a step in which a carbocation is formed. This is going to be the RDS step. If the rate of formation of carbocation is very fast, then of course the rate of SN1 is also going to be very fast. Now, since at this sp3 center we have so much bulky group, we have three tertiary butyl groups, this is present in a very much high strain. This system wants to release this type of steric hindrance, so the molecule, this bond is going to break very fast and it will generate a carbocation which is going to be sp2 hybridized. Now the repulsion is going to be released because this molecule has now become planar in structure. Here it was tetrahedral in structure, sorry, in hybridization. Now it has become sp2 and now the shape has become trigonal planar. That's the reason the D option is going to be correct. The rate will be fastest for the D1. Of course, the steric crowding is dominating. On this same concept, UPSC geoscientist has asked the question, one question of organic chemistry this year only. I don't remember the exact question, but the question has came on the same concept only. Okay. Now those days where has gone, where on the basis of carbocation stability they are going to ask you the SN1 rate. You are not giving any JEE or NEET paper, you are giving NET, GATE and SET exam. Of course, something new is going to come. Let's see the second question. Again, this is also a very nice one. Again, a stereochemistry has been involved here. They are saying that the mechanism of the mechanism and the product form in the following reaction. First of all, they are trying to ask you what is the mechanism of the reaction and what is going to be the product. Yes, tell. We have water as a nucleophile here and you need to tell the mechanism and the product. Think very carefully. You need to draw the molecule also if you think so. It will be wise for you if you draw the molecule. Hmm. Lots of you are saying B option, B option, B option. Suprabhat, Suprabhat, Camp Pacific. Option B, SN1. Option D, option B, SN1 racemic mixture. It can attack from above or below. Okay. Rashmi Jain saying B. Sorry, Rashi saying B. D, D, C. They have created a confusion in your mind whether we should form a racemic mixture or whether we should go with a D option. Two options can be eliminated very easily. SN2, SN2, eliminated. Because of course SN2 is not going to take place. It's very difficult to attack from the backside and to eliminate the Br, and since this center is also a 3-degree center, it is going to prefer a SN1 reaction since the carbocation will be very stable. Now, if you observe this molecule and if you try to draw a chair form for this, what you are going to have is, you have a scenario something like this. Three chair forms joined to each other. These are the three centers which are going to have a hydrogen, one here, one at this center and one at this center. Now, this is the center which is going to form a positive charge. Correct? Now, when you will be proceeding with this reaction, it will be very difficult for the water molecule to come from the downward center and to attack the p orbital lobe, which is surrounded by so much of crowded region, or we can say surrounded by the three-membered ring, whereas it will be very easier for it to attack into the lobe which will be present from the top side. So that's the reason when we form the product in this case, only the product of above the plane approach is possible, and from below the plane It is not possible. So they have drawn a SN1. Of course, we are going to go with SN1, and the OH which is present above the plane will be the correct answer. They have played with your concept. So if a question comes from a simple SN1 reaction, don't take it on an easier side. See whether something of stereochemistry or some cavity or something else is not playing an important role. If you are in hurry, definitely you are going to do negative in such questions. If a question has been asked in your CSIR NET exam, then please do look at the question very carefully. Try to see whether something else can happen or not. If you are full confident, then you can go with the option. Of course, the option number B is going to be wrong and the option number D is going to be correct. Got it or not? So this is a kind of a question which is out of the blue. Generally, an SN1 reaction does not show like this. They form a racemic mixture. But that is the scenario when we deal with simple aliphatic systems. They have chosen a question which is which can be a chair, which can be drawn into a chair form, and of course the attack is going to be very complicated. Got the concept? What I am trying to convey is look at the question and carefully. Okay, that's the point I am trying to make here. Yes, below the plane the cavity is forming, so this type of attack will be not favorable. Attack is going to take place from the top side only. Okay, option number D is going to be correct. Now, moving ahead, I will be coming back to our concepts which we were discussing. If you remember, we have finished our case number 3. For now, we will be starting our case number 4, that is our NOR-Borean systems. There is a lot to know and learn in this case number 4. See, in case number 4, we have seen that we are going to get a NOR-Borean system with a double bond, let's suppose, present here, and a OTS group, which will be our living group. And of course, we have a ACOH, which is going to act as a nucleophile, and we are forming a product. Let us compare this starting material with a different starting material also, where we do not have any double bond. We have only our OTS as a living group and a hydrogen, and this is our ACOH, again a nucleophile. In the first scenario, since we have a alkene present here and we have a OTS, of course they both are anti to each other, so that the double bond electron density can attack into the sigma star orbital. A question can be asked in 2 marks. Tell me which are the molecular orbitals involved in these two in this type of attack. See, since OTS bond is breaking, of course the OTS sigma star orbitals are vacant. They are going to accept the electrons which are coming from the pi bond. So always empty sigma star orbitals are going to be involved from the substrate, or we can say from the OTS side. And from the alkene side, the filled pi orbitals are going to be involved. Why? Because they have the pi electron density. If alkene is donating somewhere, it will be using those electrons which are in the pi bonding molecular orbital. That's the reason if a question asks you, if the examiner asks you, then you will be telling empty sigma star and filled pi orbitals are involved here. We can say they are the frontier molecular orbitals. They are the molecular orbitals which are involved in the reaction. Got it? Now, what happens once the attack takes place? Sometimes it becomes very complicated to understand. If you will complicate the question, it is going to become complicated. See, we have two centers at the alkene. Let us name this center A and this center B. You can say the attack is possible from either A center or either it is possible from B center also. If we attack from the A center, the bond will be forming here and the positive charge will be forming at the B center. Correct? So I am drawing this bond because we have attacked from the A center. Now someone says that no, I don't like this attack. I will be attacking from the B center. I will say okay, no problem. Let's attack from B center also. Now, if we attack from the B center, the solid line is going to be present here. Now, the positive charge is going to be present at this center, at the A center. So, these are the two possibilities. One third possibility can also be drawn. Let's suppose the sigma electrons which are present in this sigma bond there are two electrons. If I move these two electrons at this center, or I move these two electrons at this center, a third intermediate can also be drawn, which will be having a positive charge now at this center, and the double bond will be present here. Of course, this is a double bond whose sigma formed when I have shifted the sigma electrons here. So these are the three carbocations which can be drawn. If I try to draw all the three carbocations into a single structure, what we called it as a resonance hybrid structure, what we are going to have is a dash bond present from this center, a dash from present from this center, and a dash bond present here also. And a positive charge is roaming sometimes at this center, sometimes at the A center, sometimes at the B center. Now this type of carbocations are not the carbocations which we study usually. For example, they are not a classical carbocation. Such type of carbocations which are rotated at three centers are called as non-classical carbocation. So this can be a question also. Non-classical carbocation. Now, some books even write that this type of intermediate is an example of three center three center two electron bonds. Three center two electron bonds. So how this is a three center two electron bond? If you remember B2S6 molecule, when you study inorganic chemistry, there you study banana bondings. Have you heard of that? Of course you have heard of that. In the banana bonding, what you have a boron center, hydrogen center and a boron center. Three centers are present there and two electrons are present there. Similarly here also, see, we have these three centers at which the carbocation is roaming, or we can say between these three centers, these two electrons are roaming. Sometimes it is present here, sometimes they are present here, and sometimes they are present here. So three centers and a two electron is roaming. So it is an example of three center two electron system also, similar to that of banana bonds which you have formed in your inorganic chemistry. Got it? Now, since when we have formed the intermediate, we have three types of intermediate. We can say them as 1, 2 and 3. Now, I can use any one of them to explain you the formation of product. Okay. So, what usually books does, they pick either one or they will pick either second intermediate, and how the product is going to be formed is, see, let me take a blank slide, then I will be able to explain you. I hope you have copied this in your notes. Moving ahead, let's suppose I have picked the intermediate that was A1 when the attack was taking place from this center. We have positive charge here. Now your nucleophile ACOH is going to come. It will attack at this center. The bonds are going to shift here and the product is going to look like a double bond which was present in the initial reactant and a hydrogen here. If we compare this product with the starting material, what we find is this nucleophile is present in the same place as that of the living group. It means that yes, we have formed the product which is of a simple retention. So of course we are forming a product which is of a retention, and that was happening in the NGP reaction also. Did you got the concept? Now, a very famous question is asked to you to compare the rate of the reactions. Let's suppose if I have a double bond present here and OTS, And in the second scenario, what I have done is double bond is here and the OTS is present at this center. Okay, and in the third scenario, I don't have any double bond and I want you to compare the rate of the reactions for all the three substrates given that they are K1, K2 and K3. Now, comparing the rate is very easy. But if someone asks you draw the product also, then sometimes it becomes difficult. So first of all, tell me what will be the rate for K1, K2 and K3. Arrange them in the increasing or decreasing order. What if I ask you about the rate? So it's very easy. Since this double bond and this sigma star orbital are very much approachable to each other, this double bond attacks into the sigma star and the OTS is removed. If I ask you the n-chimeric assistance, n-chimeric, I have introduced this term in the yesterday's lecture, assistance is applicable or not? So yes, it is applicable and the pi bond is responsible for this n-chimeric assistance. Definitely, sir. If I talk about, let's suppose K2. If I talk about K2, then whether the n-chimeric assistance of double bond is possible or not. Whether the double bond is eligible for the attacking into the sigma star or not. Tell me fast. Should I tell that the n-chimeric assistance of double bond is taking place here? No, we can't say that. Why? Because the sigma star orbital is at the other side. Actually, the real picture behind is that here the n-chimeric assistance is taking place but of sigma bond. Let's suppose examiner has twisted the question and he has asked you to draw the product in the case of second substrate. Then what you are going to do? We usually study the rate comparison, but we don't study what is going to be the product for the substrate. Then when you form the product, you need to involve the NGP of sigma bond. Then only the product will be formed. Of course, Anju, since they are not anti-periplanar to each other, they are not anti to each other, NGP reaction is not going to take place. Instead, a sigma bond NGP take place. In the last scenario, when we have K3, since we don't have any double bond which can stabilize the carcy, we can explain this intermediate by a second effect also. How we usually explain this as, we say that if OTS is a living group, then there is a quite good possibility that it will be removed, and if it goes out, of course the positive charge present here can be stabilized with the help of this double bond. This is the second way to explain this question, but it becomes important to know that also that yes, NGP do participate here and sigma bond NGP is taking place. If the examiner will go into the depth of the concept, he will be asking you about this. If he does only want to tell you the rate of the order, then you can go by this. Yes, the double bond will stabilize the carbocation, so the rate is going to be K1, the fastest one. Then comes your K2 and the K3 is going to be the slowest one because no such factor of stabilizing the carbocation is present here. Got this? If I explain you the product also, how the product is going to be, so actually what happens, this sigma bond attacks into the sigma star orbital and the OTS is removed from this center. Okay, now how the product is going to look then? See, since we have moved the sigma bond, it must have been breaked and it would have been formed at the new center. The bond must have been formed somewhere here. Sometimes it becomes very complicated to imagine the product, but if you do the numbering, you will not face any problem. Now, since the bond has breaked from this center, we will be having a positive here. A allylic carbocation is also present here. So now when you see and do the numberings at the centers, you have 1. Let's suppose this center was 2, this is 3, this is 4, and this is 5. So we are going to have a 5-membered ring along with a 4-membered ring, which is like this. See, if this is 1, let's suppose this is 2, this is 3, of course this is going to be 4. Now we have a positive charge and a double bond present here. Now if we have chosen acetic acid as a nucleophile, it is going to attack at the center and the product will be like this. Usually books do not give you about the product, information about the product. They generally explains you the rate order, but it's important for you to know the product also. CSIR NET exam can ask you the product also. Understood? There are two concepts here. First, the rate order, and second, how the product is going to be looking. Is it digestible to you? Akansha is asking, sir, whether in the third structure NGP can occur or not. See, Akansha, there is very rare chance, first of all, to be that the question will be asked for the third scenario. But yes, books have reported such things that sigma bond NGP can take place on the third case also. But since the carbocation which is going to be formed after the NGP will not be an allylic one, so the rate will be not as that fast as compared to the other one. Okay, if someone asks you whether it is possible or not, you can say yes, it can be possible because sigma bond can attack into the sigma star orbital, but it will be not as that good that happened in the previous case because the carbocation form there was at the allylic center. These are the things which are of really depth. When you will explore lots of book, then in some book you can get such concepts written. Got it? So this question is really important. Generally, they ask the rate of the substrates, but it's important to know about the product also. Generally, no one tells you about this because they also don't know about this. So how they are going to tell you? If you want to go into the depth of this concept, you can check an Indian author book. I remember the book name is either Jagdamba or either P.S. Kalsi. These are the two Indian authors books they have in which they have discussed something about this. And of course, the language will be also little bit easier if you want to understand the whole concept. Okay, moving ahead. Yes, Jagdamba Singh, not of pericyclic or photochemistry. There's a different Jagdamba Singh also for reaction mechanism, and for one book is more of reaction mechanism, that is P.S. Kalsi. That books also explains you about the P.S. Kalsi comes for the stereochemistry one also, but not that. I'm talking about the particularly which comes for the reaction mechanism topic. Okay, you can get few glimpses of these concepts in that book. Moving ahead, there are lots of questions being asked on the same concept of rate comparison. Let's suppose I have some more questions. We have a double bond present here and a OTS and a hydrogen. Let's suppose we have two double bonds at both the sides. A one double bond present here and the OTS and hydrogen. If I say this goes via rate of K1 and this goes via rate of K2, then what do you think? Whose rate is going to be fast? K1 or K2? Whose rate is going to be fast? Think wisely and then answer. Don't be in hurry. A mixed answers are coming. Someone are saying that it will be K1. Some are saying that it will be K2. See, for the first scenario, I see that the sigma bond, the lone pairs, the pi electron density of the double bond can attack into the sigma star orbital and the OTS will be removed. Of course, the n chimeric assistant for the double bond is applicable here. Similarly, here also this double bond can attack and the OTS will be removed. Now, when I attack from any one of the center, we know that an intermediate is formed. Three intermediates are formed in which one of them is going to look like this, where the double bond will be present here and a positive charge here and a double bond will be present here. Similarly, we can explain this also by using the third intermediate which we have drawn. A double bond will be present here and a positive charge will be present here. A time will come then when both these substrates can form these two intermediates. Now in the first scenario, this positive charge has a double bond here also, has a double bond here also. They are now indistinguishable. Both of them can participate in stabilizing this carbocation. So of course, there's a greater chance for the stability for first one. So the rate of reaction for the K1 will be faster as compared to K2. Got this or not? Did you got? And chimeric assistant for double bond is applicable in both the cases, in the first one also, in the second one also. So on the basis of that we cannot comment, but on the basis of intermediate stability, yes, we can comment. Now let's suppose we have again a norborane system and I have drawn a three-membered ring, OTS and a hydrogen. In the first scenario, the three-membered ring is present at the endo position, and in the second scenario, this three-membered ring is present at the exo position. I want you to comment on the rate of the reaction for the K1 and for the K2. Whether NGP is going to take place or not. If it is going to take place, then whose rate is going to be faster? For K1 or for K2? Think, think and answer. Don't forget to like the session. If you love what I teach and if you understand what I teach, then please give your show your support in the form of comments, in the form of liking the video, or you can subscribe the channel also if you are new here. Three-membered ring, more rate, cause high strain in ring, sigma bonding, more reactive. Sigma bond is present in both the scenarios. If you look carefully, we have sigma bond here also, a three-membered ring. We have a sigma bond here also. But there is something new in this concept. See what happens when we look at a three-membered ring. We have a 60-degree angle present here, and if we see the hybridization of this center, this is sp3. Can you tell me what's the hybridization of a tetrahedral, sorry, what is a bond angle in the case of tetrahedral sp3 hybridized center? What should be the bond angle in a tetrahedral system? 120 degree is in trigonal planar campacific. I'm asking about tetrahedral. It's usually, sir, 109 degree, 24, yes, you can say that also. But we have kept this three-membered ring at a 60-degree angle. The bonds wants to be at 109 degree and we have kept them at 60 degree. So you can understand the amount of pain they are in. The strain which they are facing is very high because they want to be get relaxed. They want to reach 109 and we have kept them at 60 degree. This is not torsional strain spread piece. This is angle strain. Torsional strain is different. So now, because of this angle strain, three-membered ring, actually every bond is curved a little bit, is bulged a little bit outside uh, towards the out direction. They are bulged in order to increase the bond angle. So here also these three-membered rings are going to be curved. For the first scenario, this curve direction will be going to will be in upward direction, and for the second scenario this curved direction is going to be in the downward direction. Since in the first one the curved direction is upward, it will be easier for it to attack into the sigma star orbital, and it will be little bit difficult for these electrons to attack into the sigma star orbital. So the rate of first one is going to be really fast as compared to the second one. Did you get this concept or not? Sometimes students get confused. They don't understand how the bond is curving, in which direction it is curving. You need to understand that. When the ring is present at the endo position, the direction of curve is upward. That is, it's towards the sigma star orbital. And in the second scenario, it is away from the sigma star orbital. It is downward in direction. So approach is little bit difficult as compared to the first one. So the rate is will be faster for K1. So this is how we explain the three-membered ring NGP. I am giving you a small question for homework which I will be discussing in the tomorrow's lecture. This will be the last question for the day. Let's suppose we have a alkene which will behave as an n-chimeric group, which will apply its n-chimeric assistance. Let's suppose in the second scenario we have a three-membered ring which is going to apply its n-chimeric assistance, and in the third scenario we have, let's suppose, no double bond system present and a simple OTS group. And in the fourth scenario, let's suppose again we have a kind of three-membered ring only, but the position will be changing. These type of questions are asked in your exam where you need to compare the rate of the reaction. Here the OTS was present at this center. You need to, if I say that this goes via K1 rate, this goes via K2 rate, via K3 rate and K4 rate, you need to compare the rate between K1, K2, K3 and K4. This question is really very important. It will clear lot of your doubt. So this is going to be your homework. Spend few minutes over this. Do not try to solve this now. We will be starting tomorrow's lecture from this question only, and there will be some more questions from the previous year which we will discuss in the tomorrow's lecture. Sir, please discuss perpendicular and bisected form of cyclopropane concentrated in any. Okay, Akansha, we will see in the coming lectures. So K1, K2, K3, K4, you need to compare whose rate is going to be fastest and whose rate is going to be slowest. Okay, thank you so much for today. I'm winding up the session here only. Tomorrow we will be covering the miscellaneous portion and also we will cover some previous year questions. Thank you so much everyone. I hope you are learning new concepts in all these lectures which I am taking, and of course your concept is getting more clear and clear if you are attending these sessions. Thank you so much. Take care and happy learning.